The outlines of our today lecture is about definitions of high entropy alloys, and why I'm saying definitions, because high entropy alloys can be defined in different ways depending on the concept you are considering, as we will see. Then we'll talk about the four core effects of high entropy alloys, or as I'm calling, the four secrets of high entropy alloys. Because these core effects give the high entropy alloys their special microstructures. Then we'll talk in details about the microstructure design strategy, which gives the high entropy alloys their extraordinary mechanical properties compared to conventional alloys. Then we'll come to manufacturing routes, applications of high entropy alloys, and finally we'll end by the future insights. What is going to be done in the future for high entropy alloys? As you know, since long time ago, all the materials engineering are looking for good combination between strength and toughness, which is not easy because both of the two properties are contradicting. When you increase the strength of the alloy, you lose toughness, and vice versa. Therefore, metal matrix composites, ceramic composites, oxide-dispersed alloys, max-phase alloys, and high entropy alloys have been developed. High entropy alloys started as research project for some students in 1996. Then in 2004, two separate teams of co-workers and Cantor co-workers published some significant results about high entropy alloys. Since this date, several papers have been emerging. Let's say, what's high entropy alloy? High entropy alloys can be defined as multi-principal element alloy, or equiatomic alloy, or compositionally complex alloy, or concentrated solid solution alloy. And we will see the reasoning for each definition. We have in the galaxy very, very large amount of elements, and you have freedom to mix these elements in your way to form high entropy alloy. So you have unlimited number of alloying. Actually, you have unlimited, because you can design the alloy as you like. You can design alloy according to your requirement. You can make light alloys, you can make ceramic alloys, refractory alloys, you can make hard alloys, soft alloys. It depends on your choice. So some people say that, okay, based on that concept, we can call it multi-component alloys or multi-principal alloys. Some others said, no, we'll call it high entropy alloys or equiatomic alloys. Why? Because the concept of high entropy alloys is you mix the two elements in equiatomic manner or near equiatomic manner to increase the entropy of the system. Why you need to increase the entropy of the system? Because if you remember the Gibbs free energy equation, if you increase the entropy of the system, you will decrease the free energy. And if you decrease the free energy of the system, you can have solid solutions. That's why also some people call it solid solution alloys. Because in high entropy alloys, our main target is to have solid solutions, not intermetallic. You can have some intermetallic, but very limited. But the main concept is to design solid solutions. Therefore, simply you can say high entropy alloys are alloys that have at least 4 or 5 principal metallic elements, and they can have equal or near equal compositions. Like, for example, we have equimolar aluminum, cobalt, chromium, copper, iron, nickel, and we have non-equimolar, as you see. We can have in high entropy alloys minor additives like carbon and boron in this alloy, but you have to be careful. The minor additives should be controlled, because if it increased more than required, it will make the system not stable, and you will not have the high entropy alloys you desire with solid solutions. You can have intermetallics, so we have to pay attention. Someone may ask, why high entropy alloys have such extraordinary properties? This is due to the secrets which I was talking about. First one is cocktail effect. as you see in the video in the beginning, we have cocktail actually. So this cocktail effect should have special properties. Second one, we have high entropy effect. You have a special system with very high entropy. So you have to think about it. Also, we have sluggish diffusion effect, and we have the most important one is the lattice distortion effect. What does the cocktail effect mean? In the regular alloys, if your alloy is aluminum alloy, you expect that it will be soft, will be deformable, and so on. If you have titanium alloy, you will expect it will be hard, will have high strength, corrosion resistance, so on. In high entropy alloys, you cannot determine exactly the properties because, for example, here, if we see, this is the relationship between hardness and X value of aluminum in this alloy. So we have copper, cobalt, nickel, chrome, iron alloy, and we add aluminum with the small additives. If we see here, the alloy up to 0.5 have FSC structure. When we add aluminum more, became FSC plus BCC solid solutions. If we add further, we'll go to BCC. And unexpectedly, the hardness increased with adding aluminum, although aluminum is soft element. So here you obtained properties which cannot be expected. That's why they call it cocktail effect. In the beginning of the video, if you remember, in the cocktail you have a color which is different than the color of all the fruits. So this is high entropy alloy. The second effect is high entropy effect. Someone may say, how high is the entropy to be high? Okay, some researchers divided it into low, medium, and high entropy alloys. Based on what? They say, if we plot the configurational entropy versus temperature, and configuration entropy is related to gas constant. So if delta S over R over 1.5, it will be high entropy. If between 1 and 1.5, we'll have medium entropy. If lower than that, that means we have low entropy alloys or even conventional alloys. Then we come to the sluggish diffusion effect. In high entropy alloys, actually diffusion is very slow. Why? Because if you see here, you have mixture of atoms, small and large and medium, arranged actually in a funny way. So the large variation of lattice potential energy among the lattice sites is high. So you have numerous low lattice potential sites in high entropy alloys, which act as traps and thus suppress atomic diffusion. If you compare here the dilute solid solution to the high entropy alloy, you have traps in your diffusion path. So imagine ants diffusing in this way. So that's why diffusion is very slow in high entropy alloys. This is called sluggish diffusion effect. The most important effect is lattice distortion effect. Why? Because, for example, if you have systems with small atoms and you add big atom like aluminum, what will happen? As you add more aluminum atoms, the atomic level increases too high. So the system has to reduce the energy. In this case, as we saw in the previous alloy, the structure will be changed from FSC to BCC. Why? To decrease the Gibbs free energy. And because of this lattice distortion, we have many dislocations. We have all types of dislocations you can expect in high entropy alloys. We have dislocation interactions. And all these dislocations and their interaction actually are responsible for the strength in high entropy alloys. So this lattice distortion effect is very important. Microstructure design strategy of high entropy alloys is very important because not all the alloys that have 4 or 5 principal elements and have equiatomic ratio compositions can form high entropy alloys with solid solutions. According to the previous studies, only carefully chosen compositions can form FSC and BCC or mix of them. Then, how to predict the phase formation of high entropy alloys? Actually, to design high entropy alloy, you have to consider the parameters that fall under rotary rule and thermodynamics. If we see here, if you mix three different elements, there are possibilities that they form single solid solution, or they can form intermetallic and solid solutions, or they even can form multiple solid solutions, depending on the mixing manner. If you see here, if you change the mixing method, so you change the system. So you can have single solid solution with intermetallics or multiple solid solutions. Rotary rule contains three main parameters like atomic size, electronegativity, and electron concentration. If we can see here the comparison between the intensity and 2 theta, which are XRD patterns of different high entropy alloys, we can see here, if we have only two elements, copper and nickel, we have C. If you add aluminum, you can have ordered BC. If you add cobalt to the system, you have normal, regular BC. If you add more elements, you can have different solid solutions. Why? Because every element we add has different atomic size, has different electronegativity, has different electron concentration, and will affect the total electron concentration in the system. So every element you add to the high entropy alloys changes totally the type of the solid solution formed. It can be single solid solution or double solid solution, ordered or disordered. It depends on the additives you done. Also, we have to take into consideration the electron concentration rule. Here, if we see the electron concentration with temperature for copper and zinc, here we can see that in certain range of electron concentration, we can have FeC. If we exceed it, for example, 1.4, you can have HCB. If you exceed it further, you can have HCB with different types. So the type of crystal here is very dependent on the electron concentration. If you see here the plot for valence electron concentration for your system, here are examples of many high entropy alloys, as you see. And you can see that in certain range of total valence electron, we have BCC. In another range, we have BCC plus FeC. If you exceeded valence electron concentration of 8, you can have only FeC. So, depending on the total valence electron concentration, you have different high entropy alloys. So, to decide the high entropy alloy, you have to calculate the total valence electron. If I need BCC, I shouldn't exceed 7. If I need mixture of them, I have to fall in this region. So be attention when you choose the elements. You have to calculate the valence electron concentration. Second thing to consider is the thermodynamic consideration of system. Why? Because the main concept, as I said, high entropy stabilizes the formation of solid solution phases. To form a solid solution, we have to decrease the Gibbs free energy. As you study in thermodynamics in the bachelor degree, here if we maximize the entropy, we will decrease the Gibbs free energy. At that time, we can obtain solid solution. Otherwise, we can obtain intermetallics. And according to the Gibbs free energy plot with composition, we can have single phase solid solution. If we have delta G or mixing entropy, or Gibbs free energy, minus 65.8. For example, decreased Gibbs free energy, we can have compounds. If we reach this level, we can have coexistence of two solid solution phases. So the value of Gibbs free energy is very important in determining the type of solid solution of your system. Some people suggested that Solid solution phases form when the atomic radius is small and delta H of mixing is either slightly positive or insignificantly negative. If we see this chart between the enthalpy and the atomic radius, we can see that in certain area I can have solid solution. Otherwise, I can have amorphous phases or intermetallic phases. They said that in the intermediate condition, in terms of delta and delta H mix, intermetallic compound compete with both amorphous phases and solid solution phases. So you have certain area of competing between the two together. But if you keep yourself right here, you will have solid solution and you will have ideal high entropy alloy. Also, in high entropy alloy, you have to pay attention. Similar to the case of steel, we have high temperature phases which are brittle and detrimental to the mechanical properties. In this area of valence electron, we have sigma bron. Sigma bron is a brittle phase. Sigma is a brittle phase like in steel. But in this range of valence electron, we don't have sigma. So you have to consider which application you desire to use. So we use high entropy alloy at lower temperature or at higher temperature. If you are going to use at higher temperature, so you must check your total valence electron and see if your alloy is subjected to sigma phase at high temperature or no. And here it's a list of the atomic purpose of elements. Here, for example, it suggested that these elements encourage the BCC type solid solution, while these elements encourage FSC prototype. So it depends on the properties you desire. These are examples, for example, for as-cast iron, nickel, manganese, aluminum, titanium, high entropy alloys. These percentages in weight percent, not atomic percent. This alloy prepared at my institute by induction melting, by repeating the induction melting process. This alloy have two phases, which changed in their percentages in the microstructure according to the titanium addition. This was 0 titanium, 1 titanium, 3 titanium. And here, as you see, you have solid solution of two phases. Some other people, Wu et al., they prepared the alloy by arc melting, nickel, cobalt, chromium, iron, aluminum, tungsten alloy. And as you see, you have two phases. They have two phases, FSC and BCC. And this is the elemental distribution of the different phases. Actually, high entropy alloy is a very interesting alloy, as you see. We have also lightweight high entropy alloys, which are based on light elements like magnesium and aluminum. Actually, the main difference is that in the literature, some researchers observe that in lightweight high entropy alloys, we have more intermetallic amount or more amount of intermetallic compared to the heavy weight high entropy alloys. Here, as you can see, we have some magnesium silicide along with alpha magnesium matrix. So don't worry when you find in your lightweight high entropy alloys some intermetallics. It's usual according to the literature. Here, for example, this is aluminum, magnesium, silicon, zinc, yttrium, calcium high entropy alloys, and it showed good mechanical properties but have more intermetallics. When we come to the mechanical properties, if we compare the specific strengths to Young's modulus for different alloys, we can find that high entropy alloys have the highest specific strengths compared to the other alloys, even compared to the titanium alloys and super alloys, which is very interesting. And the good thing is that we have this high specific strengths over wide range of Young's modulus. So you can choose the Young's modulus you need according to your application, and you will still keep the high specific strengths. Why you have such specific strengths and this variety of Young's modulus? Because as I said before, the properties of high entropy alloys can be controlled. As we remember, this is an example of aluminum. When we add aluminum, with little additives and increased one by one, which changes the structure completely from FSC to BCC. This means the properties totally changed. So the control of the properties on high entropy alloys is very good, and they can lead to extraordinary properties actually. Some people give example for ductile refractory high entropy alloys, and it's very strange when you hear ductile while we have refractory, which is very interesting actually. Some people suggested this interested block of elements to have single BCC solid solution, and in a reported research, they could obtain molybdenum high entropy alloys with 40% ductility, which actually is very high percentages of ductility for a refractory high entropy alloy. In another research, eutectic high entropy alloy dual phase soft and hard solid solution. We have both of the structures. We have FSC and we have BCC. The green one is FSC and red one is BCC. But it's ordered BCC. It's called B2 actually. If we see here, we have like interchanging phases, one soft and one hard, which is very good for different applications, like load bearing applications, wear resistance, and so on. Here also we can see that in high entropy alloys, similar to the conventional alloys, we can increase the properties by cold rolling, which is very good if we need to acquire higher strength. Of course, in high entropy alloys, it's better to study the microstructure by transmission electron microscope, because most of the features that give the properties to the high entropy alloys cannot be seen if you don't have transmission electron microscope. So it's very important, especially if you design new alloy and you need to reveal the reasons behind the good properties, you have to use transmission electron microscope facility. If you compare the hardness of high entropy alloys to the Hast alloys, super alloys, and steel, you can find that high entropy alloys acquire the highest hardness among the other alloys. And of course, hardness is related to strength. That means these alloys also have high strength. Another important thing is the strength at high temperatures is very important for some applications like aviation industry and so on. If you compare here the yield strength at different temperatures for two high entropy alloys to the super alloys in Cornell and Heinz, we can find that high entropy alloys can extend its lifetime to higher temperatures. It can extend its strength and keep its strength to higher temperatures. So it's very good, as I told you, in high temperature applications. Also, high entropy alloys, similar to the regular alloys, can be modified by heat treatment. So the increase can be enhanced further by heat treatment, which is very good. And this is an example of different alloys that acquire higher strength with temperature of aging. Then we come to the practical part of the lecture, which is manufacturing routes. Some people divided the manufacturing routes into gas-based, liquid-based, and solid-based processes. But here I followed the other type of classification, which is according to the produced product. For example, high entropy alloy powders, which is zero dimension, can be fabricated by ball milling. High entropy alloy fibers can be fabricated by mill spinning. Two-dimensional high entropy alloys like coatings and films can be fabricated by laser cladding, magnetosputtering. For 3D bulk high entropy alloys are fabricated by casting methods. First is to fabricate zero-dimension high entropy alloys by mechanical alloys. You have to follow the steps for powder metallurgy, which is powder mixing and centering and compressing and so on. Here, example of mechanical alloys. This is a high energy ball mill in which the particles strike together. So there is kind of fracturing, cold welding occur. So the particles are combined together under this interaction in the high energy ball mill. For example, in the high entropy alloy nickel, cobalt, iron, chromium, or aluminum. And another type, planetary ball mill. In this type, the direction of rotation is changed every half an hour. So you have the particles strike together, we have impact shear compression fraction, then you have plastic deformation fraction and cold welding. This is a metastable high entropy alloys produced by high energy ball milling. Also, spark plasma sintering is one of the known techniques to produce high entropy alloys discs, for example. And this is a high entropy alloy produced from multiple powder by synthesis and densification. High entropy alloy fibers can be processed using melt extraction. Here we have the charge into the crucible and surrounded by induction coil. Once the melt is ready, it's exerted on the copper wheel, moving copper wheel, so you have your fibers. For coating also and films, one of the famous techniques is a sputtering technique. Magnetosputtering technique depends on precipitating particles, which are target atoms, onto the substrate under power supply. So this is the actual shape of the magnetosputtering. Here you have your substrate, you have the target atoms by applying power, you have the target atoms move to the substrate. One of the most famous techniques also is the laser cladding, because by laser cladding you can have net shaping and you can control the rate and temperature, so you can obtain films and coatings or claddings over your product. Plasma spray process, as we said, also is a very famous technique in which the particles are molten and deposited on the substrate, as you see here. Then we come to my specialty, which is processing by casting technique. Casting technique is divided into melting methods, solidification methods. Why we divide? Because solidification methods is very important in controlling the as-cast microstructure. As melting methods, we'll talk about arc melting, resistance melting, induction levitation melting. In solidification methods, we will talk about high gravity, copper mold structure, and bridge-ion solidification. The most important or the most famous melting method for high entropy alloys are arc melting method. In this method, we have the charge placed into the melting pot, and when the electrode comes very close to the charge, and the arc is generated, and this arc melts the charge. And of course, this method is suitable for high melting point elements. Like here, for example, you have chromium, iron, vanadium, tantalum, tungsten, high entropy alloys. Of course, it's not suitable for the low melting point elements. The high entropy alloys produced by this method showed high yield strengths compared to super alloys at higher temperatures. This is a vacuum arc melting facility at my institute. We have here the chiller, the control unit, melting chamber. Inside this melting chamber, the charge is put into the crucible pots, and this is the melting electrode which is used for melting. Once the melt is ready, we wait to solidify, then we move to melt again. Why we melt again? Because repeating the melting process homogenizes your sample. How many times should I repeat? Some people say 3, some 4, some 5, some 6. No, it's not important how many times. The more important is to obtain homogenized samples, because the alloys and elements differ in their viscosity, in their fluidity. So it's up to your sample actually, up to your design system. Some others used resistance furnace for low melting point alloys like aluminum and magnesium alloys. They use the steering to mix the components very well, and they cast under vacuum gas to keep the melt away of oxidation. The second important melting method is induction furnace, induction melting. In this method, the charge is inserted into the crucible and surrounded by induction coil, and this method is suitable for melting most of high entropy alloys, except for the refractory ones, which require much higher temperatures. At my institute, we have two facilities. We have induction melting facility in open air, and at that time we use non-reactive high entropy systems. For reactive high entropy systems like titanium biomedical high entropy alloys, we use vacuum induction melting furnace to avoid oxidation. The fourth melting method is induction levitation melting. In this method, the charge is heated by eddy current, and then we obtain large sample, maybe 1 kilogram or more. Here we have solidification methods. According to the classification, if we have a slow cooling rate, we can have dendrites, interdendritic structures. We can have precipitation. We can have segregations for different elements in the matrix. If we have high cooling rates, we can have polycrystalline alloys. If we increase further the cooling rate, at that time we can obtain single crystal. For solidification methods, there is a method called high gravity method. It's not frequently used, but I have to mention it because it's in the literature some people used. For example, there is a group of researchers used aluminum, cobalt, chromium, iron, nickel, and solidified using these methods and obtained a single phase FCC, and with aluminum addition change it to BCC as we explained previously. In this method, they obtained the elements and oxides and heated in a graphite mold using tungsten coil, and once melted they apply the rotation or the centrifugal force. Then they have high entropy alloys with graded structure. One of the well-known methods, the copper mold suction method. In this method, after we melt in arc or induction, we pour in a water-cooled copper mold to control the cooling rate. At that time, we can control the temperature of water that cools the mold and obtain the structure, of course, based on the cooling rate. The most important method is the Bridgman solidification method. This is advanced solidification method for superalloys, and it's used in some critical parts in the airplane. Here, the crystal structure is, we have single crystal actually here, compared to the directional solidification in which we have several grains in one direction, and to the conventional equiaxis solidification. In case of Bridgman solidification, we insert the grain selector, which is prepared by investment casting by wax. And when we insert this seed in the way of the melt being go out of the furnace or of the melting chamber, this seed select only one grain, as you will see. Here, this is the real photo of the Bridgman system. This is the melt being cooled and drawn. It is schematic representation of the melt going out of the Bridgman system. In the beginning, we have ascast dendrites, then we have equiaxis grains, then columnar crystals, then the seed, which is fabricated by wax, as I explained, select only one single crystal. And of course, we have to be cautious in this seed which we insert, because it should be suitable to select only one single crystal to keep the structure of Bridgman solidification method. Finally, you come to applications of high entropy alloys. Someone summarized the applications in this nice circle. If we look to this nice circle, we can find that high entropy alloys can be used as shape memory alloys, and can be used for gas storage and energy storage materials. Also, can be used as catalytic materials and superconducting materials. They have used in the radiation protection in nuclear applications as magnetocaloric materials. So many applications are found for high entropy alloys actually. Is all of this because of its four core effects, which give it special properties and special applications. Here, if we look to the specific strengths with temperature for high entropy alloys, the first application that come to our mind is aviation industry. Some parts in the aeroplane should keep strength at high temperatures. That's why high entropy alloys are favorable in this case. Some applications need high fracture toughness while keeping good yield strength. If we look, we can see that high entropy alloys are on the top of the alloys to do so. In nuclear applications, sometimes burst occurs in the pipes, and to make repair for this burst, they apply high entropy alloys by cladding technique. So high entropy alloys prove the efficiency in repairing the nuclear pipes. Also, high entropy alloys are used as fusion plasma facing materials. They have thermal shock resistance. Some other high entropy alloys were designed as irradiation resistance and proved good creep resistance. In aerospace applications, as we said, sometimes it's used for its oxidation resistance characteristics. High entropy alloys also proved success in using as hydrogen storage materials. If you see here the comparison between the hydrogen absorption and temperature for different high entropy alloys, you can observe how efficient is these alloys to be used as hydrogen storage materials. Also for biomedical applications, our polymer titanium alloys as biomaterial is its high elastic modulus. Here in high entropy alloys, by controlling the valence electron, we can have low Young's modulus, which is close to that of the bone. And we have groups of high entropy alloys from which we can choose. So we can choose the alloy which is suitable for example, for implantation in the body. So it's very good in this application actually. Some other tested high entropy alloys for corrosion resistant applications and proved good efficiency, better than nickel alloys and stainless steel. If we talk about the future insights of high entropy alloys, actually upon surveying the published articles, we found some points are missed. For example, very limited research found on the fatigue, creep, wear, and deformability of high entropy alloys, which are very important properties, especially in load-bearing applications. Also, another interesting point is no one revealed the role of the interstitial elements like nitrogen, oxygen, hydrogen, and high entropy alloys, especially hydrogen, which cause hydrogen embrittlement in the regular alloys. How can it behave in high entropy alloys? Also, careful assessment is needed between the microstructure, heat treatment, and properties of promising high entropy alloys. We need also easier methods to fabricate three-dimensional bulk high entropy alloys for different applications. Here is must-read reviews about high entropy alloys. Why I'm saying must-read reviews? Because if you start reading on high entropy alloys, on different alloys, different subjects, you will get lost, actually. If you start by reading a nice book like this one, or some reviews which are very good and very systematic, you will have background first. Then you can read the rest of articles. This actually will give you a very good idea about high entropy alloys. Here in our presentation, everything was so short actually. High entropy alloys is a very large topic. I suggest that you work on high entropy alloys because it's nice group and the new group of alloys. And we need you as researchers, as future researchers. I encourage you to find industrial applications of this alloy. How can we fabricate cast three-dimension high entropy alloys? And in the end, I'd like to say thank you so much for your attention. But this is not the end, actually. I welcome all the Japanese students to contact me, to cooperate together, to prepare sample and make research together. You are welcome anytime. And these attached are my emails, institutional one and personal one. And thank you again.